In this explainer, we're diving straight into one of the most massive ecological and engineering paradoxes of modern aviation. You see, for decades, the aerospace industry has been locked in this kind of impossible struggle. They desperately need to slash vehicle weight and cut carbon emissions, right? But to do it, they're completely relying on incredibly heavy, toxic, and totally unrecyclable synthetic materials just to get off the ground. But what if the secret to building the ultralight, ultra-strong aircraft of tomorrow didn't require drilling for more oil, but actually just planting a seed?
It sounds like a total trick question, right? Because on one hand, you've got this messy, organic farm with dirt, sun, and rain. And on the other, you've got a completely sterile, high-tech aerospace lab dealing with vacuums, cryogenic freezing, and cutting-edge physics. And no, we're definitely not talking about a plane getting high in the wrong way. But thanks to an absolutely massive leap in material science, these two completely different worlds are colliding in a big way. Think about traditional synthetic composites for a second, things like pan-based carbon fiber. Yeah, they give us incredible strength, but they leave us with a really heavy, toxic reality. These materials come straight from petrochemicals, they take an immense amount of energy to produce, and they're notoriously hard to recycle. It's basically creating this colossal ecological debt. But against all of that, we have the light and sustainable promise of biology. And surprisingly, the exact molecular architecture we need to replace these toxic synthetics, it's literally emerged from the byproducts of an ancient crop, industrial hemp. Section 1. The modern aviation problem, the ecological and engineering paradox. Section 2. The nano secret of hemp fiber, from agricultural waste to molecular supermaterial. Okay, let's dive into this, because this number is just mind-blowing. For years after the hemp harvest, the woody core of the plant, which is called the hurd, well, it was mostly just tossed aside as industrial textile waste. But modern science has zoomed way, way in on these discarded stalks. When you process them right, the structural fibers extracted from hemp are roughly 10,000 times thinner than a single human hair. 10,000. Yet they act like a microscopic biological rebar. It's this incredibly intricate natural scaffolding that gives you immense strength without any of the bulky weight of traditional metals. Let's zoom in even further to the micro level to see how this actually works. We're talking about cellulose nanocrystals, or CNCs. Picture these as highly ordered, densely packed chains of glucose with almost zero structural defects. Because of the super high density of hydrogen bonds inside this crystalline structure, CNCs can hit a tensile strength of up to 7.5 gigapascals. That completely rivals industrial carbon fiber. And they boast a Young's modulus, which is basically how we measure stiffness, of 130 to 150 gigapascals. Nature has basically engineered a flawless structural component right down at the atomic level. But, how do we actually get from a literal plant stalk to a rocket component? Well, here's the exact closed-loop green alchemy process. Step 1 is chemical preparation. This is where alkaline treatments strip away the lignin and hemicellulose, kind of like the natural glues of the plant. Step 2 is hydrolysis, which uses super precise acidic or oxidative breakdowns to isolate those nanoscale crystals. And finally, step 3 is mechanical processing. They use ultrasound or intense grinding to disperse these pristine nanofibrils so they can be mixed perfectly evenly into aerospace polymers. Section 3. Armor for extreme conditions, surviving the vacuum, the heat, and the cold. During any flight, composite materials face 3 extreme rapid-fire threats. First up, the terrifying drop in atmospheric pressure at high altitudes. That causes structures to expand, which leads to hidden, absolutely catastrophic microcracks. Second, if you're flying a hydrogen plane, your fuel tanks have to endure the cryogenic cold of liquid hydrogen at negative 253 degrees Celsius. At that temp, normal plastics just shatter like glass. And third is delamination, which is exactly what it sounds like. The layers of the composite physically peeling apart under the massive stress. So here's how our hemp biocomposite completely neutralizes those threats. The nanocellulose basically builds a dense 3D percolation network right inside the plastic. If a microcrack even tries to form, it instantly hits a nanocrystal and just stops dead in its tracks. It's a process engineers call crack bridging. On top of that, because these nanocrystals have near-zero thermal expansion, the material simply doesn't shrink or get brittle, even when it's holding liquid hydrogen at that negative 253 degrees. And thanks to some active hydroxyl groups on the fibers, they chemically bond to the resin, stopping that delamination issue from ever happening. Section 4. Lighter, stronger, more efficient, outperforming traditional aerospace materials. Now, what's really interesting about this comparison is the sheer dominance of the biocomposite across basically every single metric. Look at the heavy density of aviation aluminum. We're at 2.81 grams per cubic centimeter, but with a tensile strength of just 572 megapascals. Carbon fiber definitely improves on that. It drops to a 1.60 density while hitting 1200 megapascals of strength. But check out the hemp biocomposite. It is the absolute lightest option at just 1.35 grams per cubic centimeter, while somehow being the strongest at 1450 megapascals. In the real world, that translates to a 15 to 20% weight reduction over carbon fiber, which absolutely skyrockets a plane's fuel efficiency. And, oh yeah, it's biodegradable. Section 5. From Labs to the Sky. Real-world pilot programs in 2026. This isn't just some far-off theoretical science fiction anymore. Look at these real-world milestones happening right now. We're already seeing these biocomposites integrated into long-range commercial delivery drones. It allows them to carry a lot more fuel without piling on the takeoff weight. They're also being built into new 19 to 40-seat regional hydrogen planes. You've even got startups like Source, backed by $3.2 million, creating nano-coatings for rockets and drones using just hemp and algae. And major partnerships are pushing hydrogen hybrid projects forward as we speak, with collaborations between companies like Fabrum and AMSL Aero. And honestly, this clearly shows why the entire industry is paying such close attention. Market analysts are projecting that the advanced natural fiber and biocomposite market is going to absolutely explode to a staggering $10.8 billion by the year 2032. Think about it. Unlike carbon fiber, which totally relies on bottlenecked chemical giants for production, industrial hemp can be grown in massive quantities in just 100 to 120 days. The scalability here is literally unprecedented. Section 6. Zero Waste Aerospace Future. The Circular Economy of Flight. So the absolutely crucial point to take away here is this closed-loop cycle. Step 1. The hemp crop absorbs massive amounts of CO2 naturally while it grows. Step 2. The waste herd is converted into high-tech airplane material, literally locking that carbon in for decades. Step 3. After, say, 30 years of flight service, a low-energy process called solvolysis safely dissolves the resin. And finally, Step 4, the pure nanofibrils are either recycled or fully biodegraded, returning safely right back into the earth. Breakthrough projects like Suchi Next and Furhi are actively proving that this circular economy works right now. Let's move to the timeline and see how this all builds over the next decade. Between 2026 and 2028, we are expecting full certification of these nanocellulose fuel systems for commercial UAVs and urban air mobility. From 2028 to 2031, we're going to see the very first regional passenger flights using green-class cryogenic tanks, which will cut emissions on short routes by a whopping 50%. And by 2035 and beyond, we're looking at mainstream aviation integration. That means the commercial passenger flights you and I take for our holidays could very soon be part of a completely carbon-negative industry. It is truly pretty wild to think about. The key to unlocking the stars and securing the future of sustainable engineering was just growing quietly in an agricultural field this entire time. I mean, if a common plant's molecular structure can totally outperform our most advanced toxic synthetics in the freezing vacuum of aerospace, what other supermaterials is nature hiding right beneath our feet? Keep that question in mind as we watch this incredible field of biological engineering unfold. Thanks for joining me for this explainer.